Welcome back for video 2 of our paper 2 preparation. As you have noticed in the first video, there's certain things that you must have in your toolkit in order to have success with this paper. There's no short way around it. The only way to prepare for an exam in maths, or the only way to prepare, is by practicing what you learn, applying whatever you learn in context. This is video 2, and we will look at circle geometry and all the theorems that you need to have in your toolkit. I must, however, stress the following. If you don't know the theorem, you are not going to use it. The more theorems you know, the more tools you have to solve any question that they might pose to you. You must be very familiar with your theorems in order to apply them. If you don't know them, you won't use them. Let's quickly look at the different theorems that we already know. We know theorem 1, which states that the line from the center of a circle to a chord that bisects the chord is parallel to the chord. The converse theorem, a line from the center of the circle that meets a chord at 90 degrees bisects the chord. Then there's a rider from these two. If a line meets a chord at 90 degrees and it bisects the chord, then that line passes through the center of the circle. We look at theorem 2. The angle at the center of the circle, subtended by an arc or a chord. Now, an arc, that's an arc, and a chord would be a line from A to B, is double the angle at the circumference. So this angle here is twice the size of the angle over there. Likewise, if an angle is drawn at the center and an angle at the circumference, don't confuse this one. It might look the same size, but it's not. This one is half the size of that one, according to this information. Likewise, the angle at the circumference, the angle at the center, is twice the angle at the circumference. This brings us to theorem 3. The angle on the circumference subtended by the diameter is a right angle. We can also state that the angle in a semicircle, because this part will be a semicircle, is equal to 90 degrees. Let's look at this. This is 180 degrees, the angle at the center. Therefore, the angle at the circumference must be half of 180, which is 90 degrees. The converse of theorem 3. If that angle is 90 degrees, then AB is the diameter of the circle. Immediately knowing this, any right angle triangle will potentially be a triangle on a circle with the hypotenuse equal to the diameter. We go to theorem 4. The angles on the circumference of a circle that is subtended by the same chord or arc are equal. Those two angles would be equal. also states the converse of Theorem 4. If a line segment subtends two equal angles at two other points, then these four vertices lie on the circumference of a circle. Let's look at the few corollaries of Theorem 4. Equal chords subtends equal angles at the circumference of the circle. Equal chords subtend equal angles at the center of the circle. Likewise, equal chords in equal circles, meaning the circles are the same size, subtends equal angles at the circumference. Theorem 5. The opposite angles of a cyclic quadrilateral are supplementary, meaning A plus C will add up to 180 degrees, as well as D plus B will be equal to 180 degrees. The converse theorem: if the opposite angles of a quadrilateral are supplementary, then that quadrilateral is a cyclic quad. Theorem 6. The exterior angle of a cyclic quadrilateral is equal to the opposite interior angle of the cyclic quad. We know that these two angles are supplementary, and we know that these two are supplementary. This one is common in both, therefore this one must be equal to that. The converse of this: if the exterior angle of the quadrilateral is equal to the opposite interior angle, then the quadrilateral is a cyclic quadrilateral. Theorem 7. The tangent to a circle is perpendicular to the radius at the point of tangency, or we call it where the two meet. The converse of this theorem: if a line is drawn perpendicularly to the radius, then that line is a tangent to the circle. Let's look at Theorem 8. If two tangents are drawn from the same point to a circle, then these two tangents are equal in length. Theorem 9. The angle between a tangent and a chord is equal to the angle that the chord subtends. Even on this side, tangent, chord, angle between the tangent and the chord is equal to the angle that the chord subtends. The construction for the proof. Remember, the diameter subtends a 90-degree angle. The converse of Theorem 9. If a line drawn through the endpoint of a chord to form an angle which is equal to an angle in the opposite segment, then this line is a tangent. I quickly make: if this angle is equal to that angle, then this line is a tangent. Or if this angle over here is equal to that angle, because there's the chord, there's the line segment, if they are equal, then this line segment is a tangent. Now, generally, you will be asked to prove that a quadrilateral is a cyclic quad. How do you do this? If you can prove that one pair of opposite sides are supplementary, then you've proven that a quadrilateral is a cyclic quad. You can prove that the exterior angle of a quadrilateral is equal to the opposite interior angle. Then you have proven that this is a cyclic quad. If you can prove that when a line segment subtends two equal angles, then these four vertices lie on a circle. Remember, a chord or arc subtends equal angles. Here is a brief example. You can look at it, study it, and try to answer these questions by pressing pause before you continue to the answer. Thank you for watching this video. I trust that the explanation served you well. For help or assistance with mathematics, feel free to get in touch with me. Contact details are displayed as